Greetings, everybody. Learning is a hobby here. In this video, I want to go over the summary for section 2.2 in John Taylor's Classical Mechanics. And as usual, I'll make a separate video where I go over the solutions to the exercise set for section 2.2. That's not going to happen today because there's actually a decent amount of exercise problems in section 2.2. So it'll take me a while to get through those. But we can do the summary for section 2.2 today. So let me bring up my notes. All right, section 2.2 deals with, again, motion of an object that's subject to a drag force. In this section 2.2, we're assuming that the quadratic drag is negligible, so we only have to consider the linear drag. And the reason that we're starting with that is because the situation is the equations that you get are easier to solve if it just involves linear drag. So if the quadratic drag is negligible, excuse me, my allergies are bothering me today. Hopefully the sniffling doesn't get too annoying. The equation for motion that we get then in terms of linear drag is given here. All right, so m times the acceleration, mass times acceleration, equals the weight of the object minus the linear drag force, so b times the velocity. Remember, that's proportional to the velocity. Here in this equation, one of the reasons why linear drag is so nice, at least equation-wise, is because if you notice the equation here does not involve the position of the particle at time t. So in other words, r double dot you can write as v dot. In other words, the second derivative with respect to position is the same thing as the first derivative of velocity with respect to time. And that's equal to mg minus bv. And this is a vector equation, right? It has two components, a horizontal and a vertical component. Or 3D, three components, but here we're just dealing with two-dimensional situation. So the horizontal equation you get looks like this: m times the derivative of velocity in the horizontal direction equals negative b times the velocity in the horizontal direction. And then this is the equation for the vertical motion: mv dot y equals mg minus bvy. All right. So here, notice that the drag force we're assuming is in the opposite direction of the velocity. So if this is our particle here, it's moving this way, so the velocity vector points like this, and the drag force points in the exact opposite direction. And then, of course, the weight of the object is pulling it down, in the downward direction. So that's mg. That's the weight of whatever the object is. Okay, like I said, one of the nice things is that in the case of negligible quadratic drag, in other words, linear, where we're just dealing with linear drag, or even if you're ignoring the drag forces entirely, the equations separate nicely like this, so they're easy to solve. That doesn't happen if you have to consider quadratic drag. So just showing you why that is down here. If you have a quadratic drag term, like we have over here in this equation, notice that you get this annoying factor of square root vx squared plus vy squared, and that makes it difficult, or I guess, I don't know if it's impossible, but it makes it really difficult to decouple the two coordinate equations here. So notice that both of them involve both vx and vy. All right. He does say in the book, we'll look at quadratic drag in a later section. It's like 2.4 or something like that. I forget what number, but we'll look at quadratic drag later on in chapter 2. All right, but in this section, we're just restricting ourselves to linear drag. So we'll start with solving the equation for horizontal motion. So if we do that, we can divide by m to solve for vx dot. So vx dot equals negative b over mvx. And then just to make solving the equation, a little bit easier, so we don't have to keep writing b over m. He introduces the parameter k, which is equal to b over m. And when we solve the equation, this is an easy equation to solve. You get an exponential. This is the solution. Vx is equal to the initial horizontal velocity, which we're calling v sub x comma 0, times the quadratic factor e to the negative kt. And then he also introduces this factor of tau, which he'll explain more why this is important later on. So tau is defined to be 1 over k, which is the same thing as m over b, because we define k to be b over m. All right, so then once we have the equation for the velocity, we can solve for the position of the particle at time t. So just integrate x. When you do that, you get to x is equal to this expression here. And then just for simplicity, we assume that the starting horizontal position is at the origin. So assume that x0 is 0. Then this c term vanishes. So x of t is equal to this expression here, how do I say this? The initial velocity in the x direction times that parameter tau times 1 minus e to the negative t divided by tau. All right, and then he just introduces some more notation here. If you let x infinity represent this quantity, the initial velocity in the horizontal direction times tau, then you can rewrite over the equation like this. It just looks a little bit nicer. And that's because this is the limiting value for x as t goes to infinity. All right. So that's the solution for the equations of motion in the horizontal direction. Before we get to solving the equations in the vertical direction, he has a little aside about the terminal speed or terminal velocity, if you like. So here we're assuming only vertical motion of the particle. And we're assuming that the downward direction is positive, and that gives you this equation here for the vertical motion. So mv dot y equals mg minus b vy. Remember, the drag force goes in the opposite direction of motion. And if we set that equal to 0, we get that the velocity in the y direction is equal to mg over b. In other words, this gives you the terminal velocity. So eventually, once the give it enough time, the particle or whatever it is, the ball or the raindrop or whatever it is, given it enough time, will approach this limiting velocity value. All right, that's called the terminal speed. This is a form for terminal speed in terms of linear drag. You get a different form if you have quadratic drag, but like I said, we're going to look at quadratic drag later on in the chapter. All right, so here, just something to notice about this formula. If you have two masses, capital M and little m, if capital M has a larger value than little m, then the terminal velocity actually is faster than the terminal velocity for the lighter object. So the more massive the object is, the higher its terminal velocity is. Also, if the cross-section of the object is larger, then the terminal velocity is slower. So here, if b prime is greater than b, then notice, and here we're assuming that m is constant for both of them. In the first inequality, I'm assuming that b is constant, so the cross sections are the same. Then in the second situation, if b prime is greater than b, then notice mg over b prime, which is the terminal velocity for the object with cross section given by b prime. Well, it's not the cross section, it's beta times the diameter, but hopefully you understand what I mean, right? The diameter is larger of the object here. This is less than this here. So the sort of like the more cross-sectional area the air sort of interacts with as the object is falling, the slower the terminal speed of the object is, which should make intuitive sense, right? If you drop a sheet of paper versus a marble, and if they have the same, mass, let's say, obviously the paper is going to eventually fall at a slower velocity than the marble, not because of the weight, but because the cross-sectional area is greater for the piece of paper, if that makes sense. All right, so then he has an example of where we use the formulas to calculate the terminal speed. insert these two situations where the quadratic drag can be ignored. So let me just read it out. For the terminal speed of a tiny oil drop in the Millikan oil drop experiment, which you can assume has diameter 1.5 micrometers or micrometers, um, and density Q equals 840 kilograms per meter cubed. Do the same for a small drop of mist with diameter D equals 0.2 millimeters. All right, so just plugging all the numbers in and everything. You do have to be careful here to make sure that all of your units match. So just be aware of that, because you want, in order to use these formulas, I want everything to be in terms of kilometers and meters and seconds and so on. So first I calculated, the value of B, which from section 2.1, if you remember, for a spherical object is given by the formula beta times D, which D is the diameter, and beta is this number that I guess is gotten by experimental. It's an experimental value, I guess. So turning that into the 1.5 micrometers, turning that into meters by multiplying by this conversion factor, you get that the value of B for the oil drop in the Millikan experiment is 2.4 times 10 to the negative 10 Newton seconds per meter. And then also I calculated the mass of the oil drop, given its density, which they told us was 840 kilograms per meter cubed. So here, just multiplying the volume of the oil drop, which, if you remember from geometry, the volume of a sphere is 4 pi over 3 times the radius cubed. 1.5 is the diameter, so to get the radius, you divide it by 2, right? So 4 pi over 3 times 1.5 over 2, all cubed, times this conversion factor to turn everything in terms of meters, because this is in micrometers here, or cubic micrometers. Multiply that by the density, and that gives you the mass of the oil drop approximately, which is 1.48 times 10 to the negative 15 kilograms. Okay, and then we can calculate the terminal velocity, which again is given by mg over b. And then here I'm just rearranging some things because we'll use this formula to make for a couple things, but let me just say what the value is. So mg over b, when you plug in all the numbers, gives you 6.1 times 10 to the minus 5 meters per second. So for the oil drop, that's the terminal velocity, right? Approximately. So deriving this formula that I have here, this is something interesting. You can notice the terminal velocity is actually proportional to the diameter squared. So again, going back to this notion that the cross-sectional area affects the terminal speed. So that's telling you something about how this works. So the V terminal for the, what was it, the raindrop or mist, droplet of mist or something, which has diameter 0.2, we can do that next. And I'm just using this formula just to make the calculation simpler for that. So all these values here, beta and the density and G, are all the same for the raindrop, right? Because we're assuming that, no, wait, it was an oil drop, right? I just realized I made a calculation mistake here because the raindrop's made out of water. I used the same density for the oil drop here for the second part, but I'll have to fix that in the description bar below. So here, let me just show you what I mean. I just realized this mistake. So over here, this Q, I used the 840 kilograms per meter cubed, but this is for an oil drop. And the raindrop is made of water, and water should have a different density. So actually this calculation is not going to be accurate because I used the wrong number for Q. Hopefully that you understand what I'm saying there. So actually, but this is the process. So you would, this is the value of D for the raindrop, but this value is incorrect. So actually, let me see if he has the actual number here in the book. This way you can have the correct number. Where does he have this written? Oh, he does. Okay, so actually this should be 1.3 meters per second if you use the correct value for Q, which, like I said, I didn't do here. So I'll give you the correct value for Q in the description bar below after I make the video, because I'll have to look it up. I don't know what it is off the top of my head. Okay, but anyway, that's how you would do the calculation. Okay, and then going on to deriving the formula for the for just vertical motion. So again, we're assuming that the particle or whatever it is just simply moving in the vertical direction. So there's no horizontal motion to take care of, and we're assuming that downward is the positive direction. All right, so then you get this equation. We can actually rewrite this over mg minus bvy. We can rewrite as negative b times vy minus v terminal. And that's because mg over b is equal to v terminal. So in other words, mg is equal to b times v terminal. And then we can separate variables and integrate to get the solution for vy, which looks like this. And then you can figure out what the value of c is by plugging v. Here I'm calling the initial velocity in the y direction v sub y comma 0. So plugging that in for vy and 0 in for t, you get this expression here, which you writes in a slightly different way just by rearranging some things. So this is the equation for vy, right? And from there, he talks a little bit about this parameter tau, why he introduces this parameter tau. He calls this the characteristic time for the object. Characteristic time, tau. So here you can use this characteristic time to figure out how long it takes for the object to, sort of like approach its terminal velocity. So when one time period tau has elapsed, the object has, and you can figure these out just by plugging the numbers into the formula that we just derived. For 1 tau, the object has approached 63% of its terminal velocity. After a time period of 2 tau, it reaches 86% of its terminal velocity. For 3 tau, 95% of its terminal velocity. And here, if the time is greater than 3 tau, you can assume that it's pretty much reached the terminal velocity. So this parameter tau gives us a sense of like how long it'll take the object to reach its terminal velocity. And he has an example where he asks us about this, and the question here involves both the Millikan oil drop and the mist droplet that we were talking about before. So the value that I have here, well, let me go through the correct one first. Let's do the Millikan oil drop, and then I'll just correct some things in the one for the mist. Okay, so find the characteristic times tau for the oil drop and drop of mist in the last example. So recall that tau is m over b, so g tau is the terminal velocity, which implies that tau is v terminal over g. So just using that and plug it, because we already figured out what the terminal velocity was, right? And using the value 9.8 meters per second squared for the value of g, we get tau for the oil drop is 6.1 times 10 to the minus 5 over 9.8, or in other words, 0.000062 seconds approximately. All right. For the mist, again, this number is not correct because I used the wrong value for the density for the raindrop. So I think the book said this was actually supposed to be 1.3. So if you plug that in, you'll get a different value here. Let me see what the book gives, just so you have the correct numbers. Here it says for the raindrop, it's approximately 0.13 second rather than 0.11. So here, this should be approximately 0.13 seconds. the mist, just using the same formula, this one here, because we already know the terminal velocity for the mist. All right, so then therefore the oil drop and the mist reach 95% of terminal velocity. You just multiply those values by 3. For the oil drop, it reaches 95% of its terminal velocity after 0.000019 seconds. And for the and actually this should be a different value here too. For the mist, I think he said this was like 0.4 seconds respectively. So this is the when any time period greater than this, the oil drop basically is at its terminal velocity. And for the mist, after approximately 0.4 seconds, the droplet of mist will have reached its terminal velocity. All right. And lastly, we can solve for the the vertical position of the object, whatever it is, by just integrating. So Vy is the same thing as dy dt, which is equal to this when you integrate. Vy is v terminal plus v sub y comma 0 minus v terminal times e to the negative t over tau. Integrate that again with respect to time, and you get here I have the antiderivative, but you get this expression here when you simplify. Okay, and v sub ter stands for the terminal velocity in the y direction, and vy comma 0 is the initial velocity in the vertical direction. All right, so that gives you the position in the y direction, which means that so here, if we assume that x0, the initial position in the horizontal and the vertical position are both 0, so in other words, the particle starts at the origin of our coordinate system, then you get the path of the particle using the formulas that we just derived. So that's these formulas here. All right, and that's essentially the section summary for 2.2. Let me just stop the screen share. So I'll post the correct value for the density of the mist droplet in the description section, just so you can redo those calculations if you'd like to. And I will be doing the exercise set for 2.2 as soon as I can. It's probably not going to get done today because I have some work stuff that I got to do also today. But I am going to make one more video today on in the cryptography book that I'm going through, just because it's a short section. So I'll be posting that today as well. So take a look out for those. And I have decided, I think, that I'm also going to, let me just show you here. I think I'm gonna, because I already actually did all of the exercises for this book in chapter 1. This is John Stillwell's Elements of Number Theory. I think it might be interesting to go through this book in tandem with the cryptography book that I'm going through, Elementary Cryptanalysis. This is the Sinkoff book, because the first 3 chapters deal with divisibility and congruences and modular arithmetic and stuff like that. So I might actually I've done all the exercises here, but I have to do the summaries for the chapter sections, which will take a little bit of time. They're not that long each sections, but there's like a bunch of sections in chapter 1. So look out for those too, because I'll be posting those within the next week or so as well. So all right, before I'm in danger of making this video too long, so before that happens, let me say thanks for watching. Please do like and subscribe if you enjoy this content, and I'll see you guys in the next video. Until that time, keep learning.